Hey everyone, we're going to go over the basics of our force unit today. And before we get started, I want to say a lot of people worry a lot about doing these problems, but I feel like not enough people worry about the first two parts of this unit, which are kind of the basics and the different forces. I think if you really work to understand the concepts in parts one and two, that the problems themselves will be much more straightforward. So the basics. Force is a push or a pull. They're measured in newtons, which are named units, and we use that name because kilogram meters per second squared is a lot to say. Forces are vectors, which means that their direction matters, and we usually talk about the direction in terms of positive and negative, although in this unit we did start looking at things that are on angles. Isaac Newton, for whom we have the Newton named, also came up with three laws that help us understand the properties of forces. First, the law of inertia, which basically says that objects are going to keep doing what they're doing unless we act on them by a net outside force. And what is a net force? It's kind of like the effective force. It's all the positives minus all the negatives. Newton's second law tells us that net force equals ma. In other words, that mass is inversely proportional to acceleration and force is directly proportional to acceleration. Things that are light are easy to accelerate. Things that are heavy are hard to accelerate. Big forces create big accelerations. Small forces create small accelerations. And finally, we know that for every force, there is an equal and opposite reaction force. All right, so let's think about some of those specific forces that we talked about. First of all, gravity. It attracts any two objects with mass to each other. Right now, we're working on Newtonian gravitation, which means we're really just worrying about the Earth and other things. And so to calculate that, we find that the force of gravity is equal to mass times the acceleration due to gravity, which is negative 9.8 meters per second squared on Earth. Cool thing, this actually works not on Earth too. You can do this on the moon or Mars. You just need a different value of G. And we also call the force of gravity weight. And I know some science teachers who are very, very, very attentive to the difference between weight and mass. Weight is the force of gravity on an object. Mass is how much stuff it has inside of it. Normal force is the force the surface exerts to support an object. Spring forces, we did a lab on this one and found that how much the spring is pulling with is proportional to how far it is pulled. So the force of the spring is kx, where k is a spring constant measured in newtons per meter. And we graphed this. And if you're in my class, I'm going to give you a hint. You're going to see that graph on this test. And that k is really the slope of the force extension graph. Friction is equal to mu times the normal force. So there's only two things that impact friction. Mu is the coefficient of friction. It's between 0 and 1, and it tells us how rough the surfaces are. Normal force, Fn, again, is the support force, but it also tells us how much they're being pushed together. And remember, the reason these two things matter is because it tells us whether they're going to interact a little or interact a lot. And then we also talked just conceptually about the difference between static and kinetic friction, that it's much harder if something is very interlocked to get it started moving than it is to keep it moving once you get it free. So starting the movement, which is static friction, is usually larger than kinetic friction. And that difference is bigger when we're looking at really rough surfaces. When we're looking at really smooth surfaces, it's much less of a difference. And then finally, we talked about two different problem types. And I think it is worth thinking about the fact that these problem types both start with the same exact equation. Net force equals mass times acceleration. Now, in static equilibrium, the object isn't moving, which means that that acceleration is 0. And so it's even a little step easier because it really means just net force is equal to 0. We talked about three levels of that problem, where one is where like only the unknown force is at an angle. And then we did 2 and 3 where more forces are at angles. For all of them, we use the same steps. You break down any diagonals into their horizontal and vertical components. We go to net force in the x direction is 0 and net forces in the y direction is 0. Add all of them up. And then use the Pythagorean theorem at the very end to recombine. When you have fx and fy, you use the Pythagorean theorem. Second law problems take it one step further. We don't know what the acceleration of the object is, and honestly, that's usually what we're solving for. I gave you three levels here as well. In first level, you know all the forces, and it's just a matter of calculating the net force, calculating the acceleration. And then in levels 2 and 3, we have more forces unknown. If it's just like one, just like gravity, then we're talking kind of a level 2 problem. If it's many different forces, including friction, we're thinking about a level 3 problem. And in all of those problems, once you calculate that acceleration, I'm probably going to ask you to do some kind of like big 3 problem with it. So what are the steps there? You calculate the unknown forces so that your free body diagram has all the forces drawn in. You calculate from net force equals mass times acceleration, the acceleration, and then you use the acceleration to solve a big 3 problem. All right, that's it for this unit. Good luck. Let me know if you have any questions.